Welcome to the Jack of all trades training channel, where I try to prepare you for your Millwright certification exam, one topic at a time. In this video, we're going to be looking at threaded fasteners. We're going to go through it. I'm going to ask you a whole bunch of questions. Some of them are multiple choice, some of them are open-ended, some of them are true or false. So as I'm reading the question, if you want to challenge yourself, you can pause the video. And please remember to like or subscribe if you want to see more of this content. The more likes and subscribes and feedback that I get, the more time I will be putting towards getting these videos out. And let's get into it. Pitch diameter of a thread is measured exactly halfway between the major and minor diameters of a bolt or a cap screw. True or false? That is false. The distance between the major and minor diameter is actually called the effective diameter. So when we're looking at that, if this is our thread and we're looking at that would be our major diameter, and then our minor diameter comes in along the bottom there. Along the bottom. What that the halfway point in between those two is called the effective diameter. Now, our pitch diameter is something a little bit different, and what it is the point of the thread where the distance between the two flanks, so this distance in between here and here is the same as the distance between the flank and the inside of the root. So depending on the tolerance and how much material has been taken off of that outside or that major diameter, we can have different tolerances or classes of fits. And that is what basically that is what the pitch diameter is on a thread. So there's an effective diameter, which is the same, which is exactly the same radially between the outside and inside, but the pitch diameter is not at that same location. It's going to vary depending on how much material. So while we're at it, some of the other terms that we have here is the helix angle. So the helix angle is dependent on the diameter and the number of threads. Not as a math equation, just like those are the two things. So if you have a bolt that's very skinny with a very small or very large pitch, you're going to have a very large helix angle. But if you have a very large fastener with the same pitch, the helix angle is going to be much more flat and very different. So then we have the root. The root is this part right inside of the thread. The crest is the tip or the point of the thread. Minor, major diameters, pitch diameter we just covered. Depth of the thread is your major diameter minus your minor diameter divided by 2. And we'll look at some of the thread angles and some of the stuff. One definition I want to talk about is pitch. Pitch is defined as the distance from one point on one thread to the corresponding point on the next thread. And we will dive a little bit more into that in a little bit. MPTF threads are considered the strongest and best dry sealing thread form. True or false? That is true. MPTF are dry seal threads, and they're used for high temp and pressure applications. MPT requires sealants. So the MPTF seals in the root and the crest, whereas the regular MPT seals on the flanks. So the MPT thread F actually just locks in, and it actually seals up right at the point where it drives in at the taper wedge. Regular MPT does the flanks. They don't actually bottom out. And therefore you need sealant because inside of that gap at the end, there's going to be a little bit of a spiral through and it will leak. Now, MPTF stands for National Pipe Thread Fuel, and the fuel is an application where there's going to be either high pressures or high temperatures. And if you put sealants and things in there, they're going to break down over time and it's not going to work. So MPTF is stronger, seals better. And I want to point out that on a pipe thread, there is a slight taper to it. Most people will know that, but it's important to know that the taper is 1 in 16 or 3/4 inch per foot. Select the threads from the list with a 60-degree profile. So the answer to that is Unified, American National Pipe, and ISO. So those ones are at the top. So we'll see here we have our, what do we got here? That's our Unified, that's a sharp V. So what we're talking about is this 60-degree angle right here. So the 60-degree Unified is the same, and yeah, metric ISO. This is a Whitworth. This is an old style British design thread where the angle on that one is actually 55 degrees. Okay, and then we have some other ones. We have square and Acme. Acme is a 29-degree angle, whereas a modified square is very small. It's like just a few degrees. And then we have our brown and sharp worm gear. So that's this one. That one has a 29-degree angle. And then we have buttress, which only transfers in one direction. You see those on sometimes like vices or things where you want to push in one direction and have kind of a ratcheting motion for it to go back, or actuators, that kind of thing. And then there's a couple more in here that I'm not going to talk too much about knuckle and dardly. But, which statement defines the allowance on a thread? Intended degree of tightness or looseness between threaded parts. Largest and smallest a thread part can be and still be acceptable. Actual measured size. Intentional difference in size between mating parts at maximum metal condition. The answer is this one here. So the intentional difference in size between mating parts at maximum metal condition. So a maximum metal condition means is, let's say we have a nut. Okay, there's a cross section of a nut. When we cut the threads out of here, there can be different, depending on our tolerance, there can be different amounts of material taken away from here. Okay, so we can have the same nut, but we've removed a little bit more material than we need to. Okay, so the actual largest the hole can be, or the most amount of material possible, we look at that, and then when we have um, our actual cap screw that fits into the nut, then we look at that, and depending on how much we remove from in the threading process for the cap screw, whether it's rolled or whether it's cut, we can have a smaller size. It can be a few thou smaller depending on, heat and temperature and just how quickly we're pumping these things out. So when we look at the allowance on a thread, we're actually looking at it from the tolerance point of view of how large the screw can be and how large the nut can be. And then when we put those two together and we screw the cap screw in, whatever the gap is at that point, that's what we're going to use to find our allowance in that. So the allowance is at the maximum material condition. So that's kind of the tightest it can be. But then it can also be, for the class of fit, can be much looser than that. So which of these designations identifies a nut? 3/8, 16 UNC 2A, 5/16, 18 UNC 1B, M10 by 125 4G, M10 by 2 8G. The answer is 5/16 by 18 UNC 1B. So the part that actually designates a nut is the B. Okay, so this is the outside diameter. This is the threads per inch. This would be your unified national coarse thread, set to designating that it's 60 degrees. And then the 1B, that 1 is the class of fit, and the B is the fact that it's an internal thread. A is an external thread. For that class of fit, 1 is the loosest, 2 is your standard or general. So 1 is just for quick application removal. Type 2 is your regular standard type fastener that you order normally, and then class 3 would be a very tight thread. What is the metric equivalent to a grade 5 strength cap screw? 5.8, 8.8, 10.9, or 12.9? And the answer is 8.8. So when we look at the head of a unified cap screw, you can see that there's 3 dashes on it. So 3 dashes you take, and this one here has 6, right? And this one here has none. So you take the number of dashes and you add 2. And that gives you the grade of the bolt. So standard grade bolts is usually a grade 5. That's kind of the most common that you'll see. Grade 8 gets a little bit stronger. When you look at hex bolts or jacking bolts or any of the hex socket head cap screws, any of the pusher bolts, things like that, those are all going to be a much higher grade. They're grade 8 or higher. So keep that in mind. when you're, torquing into some regular mild steel that you can strip threads, things like that. But um, the standard for a grade 5, the metric equivalent, you'll see stamped on it is 8.8. And that's the first way that you can figure out if a cap screw um, is ISO or it's a unified thread style. A grade 5 bolt has a strength of 120 psi. And what that means is if you take the bolt, okay, so if this is our cap screw, and we take it and we cut it and we look at it from a cross section. Okay, so we're looking at it from on the end here. If we look at the whole surface area of this, and let's say that it equals equivalent of 1 square inch. If it has a cross section of 1 square inch, which we're just basically taking the minor diameter, so whatever, you don't calculate from the outside diameter, you calculate from the minor diameter, and we figure out the surface area of that, pi r squared stuff, and it comes out to 1 square inch, that means that it has the tensile strength to be able to hold, if we were to pull on it from both directions or put it under tension by tightening a screw, that it will withstand 120,000 pounds of force. Okay. So that's for a regular grade 5 bolt. The grade 8 is 150,000 psi. And then for the socket head cap screws, it's 170,000 psi, or kips, as engineers would say. Okay. So those are the different grades of bolts. What inspection instrument is used for direct measurement of an external thread? Screw thread micrometer, thread ring gauge, thread snap gauge. The answer is a screw thread micrometer. So there's micrometers where you can adjust or you can replace the anvil and the thimble with different pieces. So that's what this is here. And you can actually go in and measure what the pitch diameter is to compare to figure out what the tolerance the fastener is. So sometimes you're buying fasteners and they're off the shelf. They've been rolled. They're manufactured a different way. But then there's other times where you're making fasteners or turning them on a lathe and cutting the threads, or the threads are being ground. And you need to know exactly what the tolerance is, especially when we get into the class 3 fits. So the way that we actually do a direct measurement, and when I say direct measurement, what I mean is that we actually have a number that's coming out that we can say that this is, exactly this number. That's a direct measurement. That's different than these ring gauge and plug gauges, which is like a go, no go type situation where you take the fastener and you take the ring gauge and you thread it in. And if it goes in, it means that it's under a certain size. So it's kind of a comparative measurement, not a direct measurement. So those are some of the ways that we can measure these. The other way that we can do it is with there's something called a 3-wire method, where you take the if you don't have one of these micrometers, you can take the fastener, and then you do 3 wires. So you put 1 wire here, and then you put another 2 wires here and here, and then you measure with a micrometer across those surfaces. Now, because we know the diameter of these wires, and we see how far down they fit, it's just a chart or a calculation to figure out exactly what the pitch diameter of the thread actually is from that point. So that's a 3-wire method. So these are just ways of just determining the actual size of the fastener. So what are the 3 hand taps found in a set? So let's say we want to cut like a 3/4 inch thread. What would be the 3 taps that we would find in the set? And the answer is a taper, a plug tap, and a bottoming tap. So the taper tap is our starter tap, and that's the first one that you're going to put. And you can see on the end here, it's actually tapered down quite a bit. So it's tapered all the way back to about here. The plug tap is kind of the next one. You can see that it only has just a few threads that are kind of tapered down, and then your bottoming tap is just the last 1 or 2. So your taper tap is actually going to be the first one that starts, and it's tapered so you can keep it nice and square, and it'll go in nice and easily, and it'll progressively cut a little bit more as it's threaded in. The plug tap will go a little bit further to get you a little bit closer. For the bottoming tap, now these bottoming and plug taps are only used for blind holes. When I say blind hole, I mean that if you have a through hole, it means that you have like a plate or something, and then you're going to cut the threads, and the tap can come all the way down and through. Whereas if you have a blind hole is just, you know, you have like a large piece and then you drill a hole not all the way through, and then you're going to cut the threads kind of down with your taper tap. Then you're going to come in and you're going to cut it with your plug tap, and then you're going to come in, you're going to cut right down to the bottom. I'll put a link here or a thumbnail somewhere with a link to one of my videos where I actually drill and tap a taper plug and bottoming and kind of show all the steps that go into that process. All right, what is the lead and thread per inch of a screw inside a standard micrometer? And the answer is the lead, or also the pitch, because there's only one start, is 25 thou. And if you take that 25 thousandths of an inch for one advance and you calculate, or you divide that into 1 inch, you find out that the teeth per inch on a standard micrometer is 40 threads per inch. Sometimes you can have multiple starts on a thread. So instead of just having one helix that's wrapped around, you can actually have multiple ones. So that's when I talk about the lead, if you take two starts, whatever your threads per inch is times the number of starts is what the lead is. And the lead is the distance that one thread will travel or advance in one full rotation of the screw thread. What is the purpose of Acme screw threads? Acme screw threads are designed for power transmission. So because of the angle, they have more material, and they're kind of squared off. They're actually designed for lifting and pushing and clamping and that kind of thing. So they are a power transmission. What formula can be used to find a tap drill size without a chart? Tap drill size is actually quite simple to calculate. It just take the diameter. So if it's a 1/2 inch fastener, or let's say like a 1 inch fastener, and the pitch is 8 teeth per inch. So the pitch from one to the next would be 0.125. In that case, a 1 inch fastener minus 0.125 equals 0.875 or 7/8. Okay, so that's just kind of the basic simple way of figuring out a tap drill size. Which statement is true about recommended torque values? They are only used by machinists, designated to give proper preload values on fasteners, apply only in the aerospace industry. So recommended torque values are designated to give proper preload on fasteners. So if we look at this, we're looking at a chart here of the amount of torque to the amount of kind of rotation or the angle that you're going to go through. So as we start to apply torque on a fastener and it's going, it kind of reaches a point where once once the fastener comes down and actually starts to engage the threads and it tightens up, there's a certain amount of preload that goes on, and then from that point forward, we call it's in alignment, and then it will go up, and the amount of torque is proportional in some sense to the amount of angle or the turning or how much we can turn that fastener. The part that's interesting is that you get up to the point where we get into the inside of the elastic limit of the fastener, and the fastener will actually stretch and stretch and stretch as we tighten it. But then it gets to a point where it's not going to return back to its original shape. So we've actually stretched it and we're starting to yield it. And then you see as the chart progresses, well, the amount of torque that we're putting on, even though we're turning it, the amount of torque starts to break and then it ends abruptly at the end here. This point on the chart is actually where we've broken the fastener. So if we apply too much torque to a fastener, we can get up in this area, and then we actually get to a point where we've actually just broken it, and we can just turn it, and that's just basically just like a fractured cap screw or bolt. Now, I point that out because we can put a torque wrench on it. We can tighten fasteners a lot of different ways. And in the chart here, over here on the right, it's saying that a torque wrench on an unlubricated bolt, even though we set our torque wrench to say 100 foot-pounds and we do a torque, depending on the quality of the threads and what it looks like, our accuracy is plus or minus 35%, which is really surprising because you'd think you'd be a lot closer to it. But there's so many different things that can affect the torque of a fastener, like the surface finish, if there's any damage to it, the surfaces that you're clamping. And so, yeah, if the joint itself flexes, like, so the joints should be designed so that they don't flex, but maybe they do. Maybe there's a gasket there. So there's all kinds of things that can apply to it. So that for a torque wrench on a lubricated fastener, we have 35% plus or minus accuracy. Whereas if we go with a strain gauge is just basically like a strip that you would glue and You measure the voltage drop across wires to find out how much it expands or contracts when we stretch it. We can get accurate to within 1%. Okay, some of the other methods for measuring that are very common is just to take a micrometer or a dial gauge and measure the bolt elongation. That will get us pretty close for knowing our torque, plus or minus 5%. So these are all just things that it just kind of just helps keep that information present while you're doing stuff to know. And you might be saying, well, plus or minus 35%, plus or minus 30%, like how can they get away with that? And the answer is it's engineered in. So when they put a bolt in there and they know that it can be plus or minus 30%, you're going to engineer or design a flange or a bolt connection to account for that variability, because you know that somebody's going to be going in there with a torque wrench and tightening the fastener. Or if in your specifications you know that we need this to be extremely critical and how it's jointed together, then in that case we need to do the measuring of the bolt elongation, or we need to use heat, or we need to do the hydraulic nut, or we need to use preload indicating washers or something like that. How are machine screws designated? Machine screws are designated with numbers from 0 to 12. So on our chart here, 0 right here, the writing is kind of small, I apologize. But if we have a 0, it means that it has a diameter of 60 thousandths of an inch. So this is 60. And yeah, I'm not going to worry about that. Okay, and number 1 is 73. So what we can say here for the number is you take the number of a machine screw, okay, and it is equal to 60 thou plus, sorry, the diameter of the number is equal to 60 thou plus the number times 13 thou. Okay, so if we look at that and we say, okay, it's a number 10 fastener, the number 10 fastener is equal to 60 thou plus 10 times 13, which is equal to 60 thou plus 130, which is equal to 0.190 thou. Okay, so that's how the designations work on machine screws. So for this class question, what does a bolt designation 3/4 inch by 16 UNF by 2-3A refer to? And there's a little bit of a typo here, but I put the right answer in here twice. So the right answer is right here and right here. So it's a nominal diameter. So the nominal diameter meaning that it's not an exact diameter, but it's darn close. So 3/4. So the nominal diameter would be 3/4, and then it's the TPI, or the threads per inch. So this is a 6/34 by 16, and the UNF means Unified National Fine. Okay, so there's Unified National Coarse and there's Unified National Fine. Unified National Coarse is stronger, it's more standard. Unified National Fine is usually done for something where you need to do some type of like a control or a setting. And then that is by 2. So the 2 is actually the length of the bolt. So this would be a 2-inch long bolt. And then the 3A refers to a class fit 3. And again, I said earlier, class fit 1 is loose, 2 is standard, 3 is a tight fit. And the A is referring to an external thread. So external threads are A, internal threads are B. So that's it for our threaded fasteners review here. I'm going to post there's a thumbnail here somewhere. I've done a video lecture on threaded fasteners, all the terms, definitions. So if you want to dive a little bit deeper, you can look at that. Otherwise, please like and subscribe to the channel if you like this content, and let me know if there's any topics or anything that I missed that you'd like to see a little bit more information on.